On a moon roughly the size of ours, there are over 400 active volcanoes. Earth, a planet with a molten core, tectonic plates, and about 70 times the mass, has fewer than 50. That ratio doesn't make sense. And when something doesn't make sense in physics, it usually means the model is incomplete. This is Io, Jupiter's innermost large moon, and it's the most volcanically active body in the entire solar system. Not by a small margin, by an order of magnitude. The standard explanation is tidal heating. Jupiter's gravity squeezes and stretches Io as it orbits. The friction from that deformation generates heat, the same way bending a paperclip back and forth makes it warm. Except the paperclip is a moon, and the hand is a planet with 2.5 times the mass of everything else in the solar system combined. On paper, this makes sense. Tidal forces are real, measurable, and well understood. Textbooks explain Io's volcanism this way, and for decades, that was considered sufficient. It isn't. But before we get to why, it helps to understand what tidal heating actually does to a body like Io. This isn't a gentle process. Io orbits Jupiter at a distance of about 422,000 kilometers, closer than our moon is to us. At that distance, Jupiter's gravitational gradient across Io's diameter is enormous. The near side gets pulled harder than the far side, and the result is a tidal bulge, a physical deformation of the entire moon. If Io orbited alone, it would eventually settle into a circular orbit where the bulge stays fixed and the heating stops. But Io doesn't orbit alone. Europa and Ganymede, the next two large moons out, are locked into an orbital resonance. For every orbit Io completes, Europa completes exactly half, and Ganymede exactly a quarter. This resonance keeps pulling Io's orbit slightly elliptical, which means the distance to Jupiter changes every orbit, which means the tidal bulge shifts, which means the interior keeps flexing. Every orbit. Every 42 hours. For billions of years, the energy has to go somewhere, and on Io, it goes into melting rock. The prediction, when Stanton Peele and colleagues published their tidal heating model in 1979, was that Io should be geologically active. The paper came out in March, 3 days before Voyager 1's closest approach. The timing was extraordinary, a theoretical prediction confirmed almost immediately by direct observation. Voyager 1 captured something nobody expected, an active volcanic plume, rising roughly 300 kilometers above the surface. First confirmed extraterrestrial eruption ever observed. The images were noticed almost by accident. Navigation engineer Linda Morabito spotted the anomaly while processing images meant for trajectory calculation, not geology. She saw a bright arc on the limb of Io and thought it might be a background moon. It wasn't. It was a volcanic plume, and it changed planetary science permanently. Tidal heating was the answer. Peale's model worked. Io was active because Jupiter wouldn't let it rest. But here's the part that gets less attention. Peale's model predicted activity. It didn't predict this much activity. When Galileo arrived in the Jupiter system in 1995, it spent 8 years collecting the most detailed data we've ever had on Io. Close flybys, infrared measurements, surface temperature mapping, gravity field analysis. And what the data showed was something that should have generated more headlines than it did. Io's total heat output is somewhere around 100 trillion watts. To put that in scale, that's roughly 2.5 watts per square meter across the entire surface. Earth's internal heat flow is about 0.09 watts per square meter. Io produces approximately 30 times more heat per unit area than our planet. A body with no radioactive core hot enough to matter, no tectonic engine, no internal combustion, just tidal flexing from a gas giant next door. HALE ran the comparison 3 times because the gap felt wrong. It isn't wrong, and the tidal heating models, the equations that are supposed to explain all of this, at their most generous, they account for maybe 60% of that energy output. Some published estimates put it lower. Depending on assumptions about Io's interior rigidity, the models can explain anywhere from 40 to 60% of the observed heat. There's a gap, a persistent, documented, decades-old gap. And it's not small enough to dismiss with a footnote. If you've ever read a textbook that says, tidal heating explains Io's volcanism, now you know what the textbook leaves out. Now, there are hypotheses. Some researchers suggest that the orbital resonance with Europa and Ganymede creates secondary tidal effects that amplify the stress in ways the simplified two-body models don't capture. The real system is a four-body problem, Jupiter plus 3 moons in resonance, and solving that completely is a different order of mathematical complexity. Others focus on the interior. The standard calculation treats Io as a mostly solid body with uniform material properties. But Io almost certainly has a partially molten layer, a magma ocean, or at least a magma slush, somewhere between the crust and the deeper mantle. And a body with a liquid layer responds to tidal forces differently than a solid one. The coupling changes. Energy dissipates through different mechanisms. The math is messier, and nobody has fully solved that coupled system. A 2022 study using Juno's microwave radiometer data found that the heat distribution on Io's surface doesn't match any simple tidal model. There are regions significantly hotter than predicted, and regions cooler than expected. The pattern correlates with something internal, probably variations in crustal thickness or magma chamber depth. But it's not the smooth, predictable distribution that a uniformly flexed sphere would produce. Each hypothesis explains a piece. None of them close the gap completely. Together, they suggest that tidal heating on a partially molten body, locked in a multi-body orbital resonance, is genuinely more complex than our current equations handle. Now here's where a different kind of video would pivot to something reassuring. Show some beautiful volcanic footage, mention that scientists are working on it, and close with a thought about the wonders of exploration. That's not what this is about, because the gap on Io is not an Io problem. It's a planetary physics problem, and it connects to everything. Every model we use to predict habitability, the calculations that assess whether Europa's subsurface ocean has enough energy for life, whether Enceladus's hydrothermal vents are real and sustained, whether exomoons around gas giants could be geologically active, every single one of those models relies on the same tidal heating physics, the same fundamental equations, the same assumptions about how gravitational flexing converts to thermal energy inside a planetary body. If those equations are demonstrably incomplete on the one body where we have the most data, a body we've studied with multiple spacecraft across 4 decades, then the confidence you place in those predictions elsewhere deserves scrutiny, not rejection, scrutiny. The kind that puts an asterisk next to quote, _1 __ and adds, our energy budget estimate could be off by a factor we haven't quantified. That doesn't make the search for life wrong. It makes it more honest. Let's talk about Loki Patera. Because this is where the problem becomes visible, even without the equations. Loki Patera is a lava lake on Io's surface, roughly 200 kilometers across. For context, that's about the distance from New York to Philadelphia, filled with molten silicate rock. It's the single largest active volcanic feature we've ever observed anywhere. And here's where it gets strange. Watch this. Loki Patera periodically brightens and dims, a cycle of roughly 500 days, though it varies. The surface crust forms, thickens, becomes denser than the liquid beneath it, and eventually overturns. The entire surface capsizes, and fresh magma is exposed. Then the cycle starts again. This has been observed repeatedly from both spacecraft and ground-based telescopes. The periodicity is real, but no tidal model predicts it. Tidal heating should be roughly continuous, a steady input of energy from orbital flexing. A 500-day episodic cycle implies something internal to Io is modulating the output in a way that has nothing to do with Jupiter's gravitational schedule. Loki Patera behaves like it has its own rhythm, its own internal clock, not a response to tidal forcing, a response to something we haven't identified yet. Juno's extended mission brought the most detailed data since Galileo. In late 2023 and early 2024, the spacecraft passed within roughly 1,500 kilometers of Io's surface, close enough to resolve individual volcanic features, map heat distribution in unprecedented detail, and probe the subsurface with microwave instrumentation that can see through the crust. The early results confirmed what the energy gap suggested: volcanic activity clusters in ways the models don't predict. There are cold zones, where tidal models expect heating. There are hotspots, where the equations say nothing special should be happening. The internal structure of Io appears more heterogeneous, more dynamic, and more complex than a tidally heated uniform body should be. Some of the data is still being processed. The full picture will take years to assemble. But the direction is visible. Io's interior does not behave the way our best equations say it should. The instinct, the natural scientific instinct, is to find the fix, adjust the parameter, add a correction term, refine the interior model, and eventually, someone will. That's how physics progresses: discrepancy, refinement, new model, new discrepancy. But there's a version of this story that's worth sitting with before we rush to the patch. We have a moon, 630 million kilometers away. We've sent Voyager, Galileo, and Juno across 45 years of missions. We've measured its heat to reasonable precision. We've mapped its volcanoes. We've watched a lava lake breathe. And the data tells us, clearly, consistently, across decades, that our understanding of one of the most fundamental energy transfer processes in planetary science has a hole in it. Not a rounding error, a structural gap. 400 volcanoes on a body that our best equations say should have considerably fewer. A lava lake with a heartbeat that no model explains. A heat budget that doesn't close. These aren't dramatic mysteries. Nobody is hiding data. The gap is published, acknowledged, discussed at conferences. But it rarely makes the headline. The headline says, Io, Jupiter's volcanic moon. The data says something different. It says, we're not done understanding this. We might not be close. The volcanoes on Io are not just geological features. They're a measurement of the distance between what we think we know and what we actually know. And right now, that distance is roughly 40%. Next time you hear someone say, we understand how moons work, remember that number. Tidal forces are real. The heat is real. The gap between them is also real. And that gap, where the equations end and the data keeps going, that's where the next discovery lives. Not in a press release, not in a textbook, in the space between what we predicted and what we found. And that's a question worth carrying with you, because it connects to something, not gravitational forces this time, but thermal ones. There were engineers who built a machine to survive a place where the atmosphere crushes steel and the temperature melts lead. They had no margin for error, no second attempt, and about 2 hours before everything failed. The way they solved that problem, with technology from the 1970s and stubbornness that doesn't fit in a press release, that's a story for next time.